This is problem number 67 in Giancoli chapter 6, page 164. The question reads, during a workout, the football players at State U run up the stadium stairs in 66 seconds. The stairs are 140 meters long and inclined at an angle of 32 degrees. If a typical player has a mass of 95 kilograms, estimate the average power output on the way up at any point along the way up. Recognizing that power is equal to work divided by time, or the rate that work is done. Let's go ahead and start with that concept here. So I've made a sketch over here. We have an initial position the player starts at. We know the mass on average is about 95 kilograms. And they end at this final position over here. We're not necessarily concerned with the 140 meters that they travel along this staircase incline on the way up. What we are more interested in, however, is the height above vertical height that they've attained here. So we can recognize that if this piece here, the hypotenuse of that right triangle, is 140 meters, we can find the height of this using sine. So let's go ahead and write that out. I'll write it over here. The sine of theta is equal to the opposite side of that triangle over the hypotenuse. In this case, we know that the opposite side of that triangle is delta y, and the hypotenuse is 140 meters. Multiplying both sides by 140, I get 140 meters times the sine of theta, in this case 32 degrees. Let me go ahead and put that in there. In this case, 32 degrees is going to be equal to delta y, and when I run that through my calculator, I get 74.2 meters. 74.2 meters is equal to the vertical height that's attained here. So now we know, a couple different ways to kind of consider this. We could say, I think my instinct is to say, all right, what's your final potential energy here versus your initial potential energy, and the change in that energy is going to be the work done. Or you could kind of look at it from the standpoint of a free body diagram, and we could say at the end of the day, the force produced by the player needs to be equal to the weight in order for him to be moving at all, in this case at a constant velocity. So we could say force times distance d, in this case against gravity, would be that vertical distance. Either way that you look at it, whether you look at it in terms of gravitational potential energy here being the work done, I'll go ahead and write that out as mgh final minus mgh initial over time. So I can say that change in my energy state between the final and the initial state, which is just going to be mg times delta h over time. I'm going to go downwards here now with this work, and then simply say that I can take the average weight, the average mass of a player, 95 kilograms, multiply that by 9.8 meters per second squared. That gives me the weight, multiplying it by that height of 74.2 meters, dividing that by the time that it takes the player to go up to the top, which is 66 seconds, will give me the power in joules per second, or watts. When I run that through, I get 1047 watts, or 1100 watts once I truncate for numerical significance. So that is problem number 67 in chapter 6.